I'm glad to be speaking after so many people that touch topics that are related to my talk, so I don't have to explain everything that I say. And what I wanted to present today is a bit of a story of, you know me mostly because of the ICAP, because I was sort of guiding the project that developed the robot. But in parallel to that, we also did some research on action recognition and on biologically plausible models for action recognition. This happened because at a certain point about maybe 15 years ago, I met Luciano Fadiga, one of the mirror neurons guy, and we started discussing, and it actually, in fact, came with the idea of trying to incorporate motor information in designing machines to recognize action, which is not what we've done all the time. And in fact, most of the results on the ICAP eventually diverge from this idea. Because it's tough, because it was tricky to actually do experiments that compete well with other more standard methods when you have also to make the robot work. So anyway, as part of our research, we certainly have a stream of this research that is looking at building biologically plausible models in general of cognition, but we can restrict the topic to object or action recognition, which are two of the key elements that we will need on the ICAP to make sure it can interact with the environment. And also, of course, we do this because maybe we get a better understanding of the brain, and also because if we can make better robots, we are nonetheless very happy. Since personally, I'm an engineer, so I like to see things that work. And maybe in the future, this hypothetical whatever scenario that I found on the web, we'll be having robots that can understand what a person is doing and behave consequently, so generate appropriate behavior because they actually understand what the person is doing. Anyway, let's go back to Fadiga's mirror neurons, or Rizzolatti's actually mirror neurons. So at that time, what he basically showed me, because I didn't know anything about mirror neurons, he visited us in the lab and we started discussing, and he said, you know, there are these neurons in the premotor cortex that are activated when the monkey either does an action or observes the same action, roughly the same action, performed by a human, by the experimenter in that case. And he said it's very specific because, for instance, a given neuron doesn't activate if you're using a tool rather than your fingers, and also specific to the type of grasp that you are generating. So it's not that you can use any type of action for that particular object. The particular neuron will be sort of responsive only to that particular action. And we thought that this was interesting, and also he told me the story that, at least what the neurophysiologists were thinking, is that these neurons represent sort of a vocabulary of action that is used both for controlling movements, but also when you have to recognize the movements. And for instance, here is an example where you see the fact that it's specific with respect to the grasp type. So this neuron is responsive to a precision grip, but it's not responsive, or less responsive for a power grasp. And on the other hand, the effector is not very important. The monkey here is using the left or the right hand, and the neuron is active nonetheless. And there are other neurons that are not shown here, where they basically activate during a particular sub-phase of the action, like opening, closing, whatever. And so these neurons were found in area 5 in the premotor cortex, and they say this is kind of the vocabulary. So they decompose the action in time, they decompose the action with respect to the effector, they decompose the action if you move in the fingers in a certain way or another. And so we try to figure out what to do, and one sort of a hypothesis to put together was kind of representing this cartoonish like block diagram where, so this is the monkey. And what happens is that in the premotor cortex, you have this action vocabulary, which eventually project to the primary motor cortex, where you have single movements, and you eventually go to connect to the muscles and activate the various muscles. Since you generate certainly perceivable consequences, this can be proprioceptive but also visual, you need sensory feedback to control or to keep the action generation along the intended path that will lead to successful action. Now, there's one point here is that if this is a sensory measurement, you have to bring it back into whatever representation you have here, which is, let's say, motoric one in the sense that it's in a premotor cortex area. And so you have to sort of build this conversion that it's important for us because it basically says that you can recycle these in case you're interacting with another person not to move, but just to compare the ongoing action that you're observing with the vocabulary of action and determining whether that particular instance is similar to an action that you generated in the past. And so this is sort of a motor-based recognition system in a way. This, again, is not super engineering. It's just a description trying to bring the results from the neurophysiology into something that we may have hoped to implement into a machine. And so at that time, this is, I guess, 2002, so quite a long time ago, we decided to do experiments where we took vision in images from cameras, so people doing actions. We didn't have any robot, no, definitely not a robot with hands. And we said, let's use people, many subjects, as a robot, a virtual robot. So we can ask people to grasp objects, we collect a database, and these can be used, we can try classifying the actions that we see. The other thing we done was, but let's imagine that this hypothetical transformation from visual data to motor data is doable. Why don't we try to build a classifier here in the motor space? Maybe this good, let's say, pre-filtering that extracts reasonable features that then make the life of the classifier easier. So we've been, I guess, a bit naive at that time in not pursuing this to a level of detail that sort of cleared beyond doubt that this was working better. I'll show you an experiment. So these are the images we got. These were the objects, not the many, and that was, I guess, one of the limitations of the experiment. And this is our visual to motor map, which was obtained simply by training feed-forward neural network using Prof to basically take the images and generate plausible joint position. Now here, motor information became actually kinematics, but that's what we can measure. We didn't have real access to the muscles. And the way we measured it is through a data glove. So we instrumented a person with a data glove with a tracker to track the position of the hand in space, two cameras sitting here behind the person. So try to create a replica of the robot that we didn't have at that time. And we built a classifier. In this case, it was a simple Bayesian classifier. And surprisingly, it worked well, especially when it was trying to check the generalization performance of the action recognition in the case where we did this pre-mapping into motor space. We thought that was interesting because I think we completed these around 2003, 2004. So it was a result of a European project. Subsequently, we tried to extend these a bit. This is another piece of results from, let's say, roughly the same period, where this is another example where a mirror neuron will be active when the monkey is observing an action, but the final part of the action is, in fact, covered behind the screen. So the screen occluding the side of the object. But the monkey knows there's an object behind the scene. So we try to see whether from this motor data, that is the tracker and the data glove, we could actually predict the posture of the hand at the end of the action. It is doable. It kind of works reasonably well. It is increasing the size of the occluder, so making it bigger and bigger. Of course, performance goes down, so the error in predicting the final configuration of the hand from an observation of the initial part of the trajectory becomes worse. But nonetheless, this is enough for doing later the classification. So it seems coherent that also the monkey doesn't need to see the entire action because you know the object that is behind the screen, you know an initial part of the movement, you can sort of imagine what's going to happen next. Okay, this was already also telling us something. So if we have knowledge about the identity of the object, which is this purple line here, we see that we do better than not knowing what the object is. So that's obvious in a sense, because if you know the object is large, you can expect the posture to be also to have a larger final configuration. I mean, the distance from the fingers should be large. And this is interesting because it sort of starts pointing out to the fact that in the premotor cortex, we found the mirror neurons, that's true, but also we find other neurons, and this was again interaction with the neurophysiologists. And the other group of neurons that you find is called canonical neurons. And these are neurons that are responsive to the size of the object and also when the monkey is grasping the same object. In this case, what happens is that basically in the experiments, they sort of force the monkey not to grasp the object, but just to fixate it. And you see, the same response, whether the monkey is allowed later to grasp the object or rather is not, is forbidden from grasping the object. This is to say that this is sort of the connection between looking at a particular object shape and the action that is needed to grasp that particular object. And sort of, as usual, a piece of information coming from neurophysiology, so to turn this into an actual grasping controller is a long way because then you have to figure out how to generate the actual joint movements. But this was also tested more recently. This is a paper by, again, Fatiga and collaborators that are working at IIT now, and which uses TMS to show the interaction between your imagined grasp type, because if you're doing TMS, you're just watching things, you're not allowed to move, and the site of, let's say, of preparatory hand movement that you just, again, watch it in a screen, and the motor evoked potential of two muscles of the hand. And now the results here, these are the 4 possible conditions. So there can be, this is a precision grip, where you actually see hands doing a precision grip before you see an object whose use requires a precision grip. Or rather, another case where you have a power grasp and also an object that requires a power grasp. And then there are 2 conditions that are actually, let's say, the negative of those, because there's a precision grip for an object that requires the power grasp. The one thing that they've been able to show in terms of the motor evoked potential is that you see a pattern. So you have a dominant pattern, for instance, in this case on the, what they call the opponent pollicis, I think, the muscle. The neurophysiologist should forgive me for this. And you see a less, let's say, sort of a scaled down pattern of activation when the situation is not congruent. So these 2 are the 2 cases where you have the precision grip or the power grasp congruent with the object you see. And these are 2 cases where they're not. So, you see the same pattern here, and also here, these two and these two. And also, if you measure the kinematics, which is the twitch you get once you do the TMS, so you see small movement of the finger, you measure how much it moves and how it moves for the values, again, for the second finger, for the fifth finger, you see again a similar pattern also in the kinematic activation. At least, again, for the situation where you have a dominance, which means situations where things are coherent. These cases are kind of more random because you see something and then you have an object that is not congruent with what you see in this is to point out the fact that also in humans, you have this interaction between the side of the hand and the object you may or may not grasp. And so we did a bit of, again, computational experiments. These were in collaboration with Barbara Caputo at India, but also with the University of Genoa, and where we work on basically combining visual and what we call grasp features for object recognition. Again, the visual part here is kind of very, very traditional in the sense that we extract sifts, we do bag of words, we build vectors, and then these are classified using standard, in this case was regularized least square, but could have been subcorrected machines, probably the results would be very similar. The one piece of information that we try to add is information about the grasp affordances. In this case, we're coded as a simple, let's say, binary number, identifying the fact that given an object, you can do, I don't know, power grasp in this way or grasp in this way and so forth. We had here in this experiment 7 types of grasp, and I think we're 5 objects. Oh, sorry, 5 types of grasps and 7 objects. And we recovered these from the motor data that, again, is acquired using a data cloud. No robot in this experiment, unfortunately. And as before, we did a mapping, so we tried to recover this information directly from vision, because at a certain point, imagine to be in a mirror-neuron situation, you learned how to recognize something, but at a certain point, if you see the action performed by somebody else, you're not doing the action. So you don't have that motor information readily available. You can try and reconstruct it with vision. And here, what is, again, can be seen, this is the database, the 7 objects and 5 graph types. Again, what can be seen is that, okay, let's see, if you use vision alone, you get a typical performance of the classifier built using SIFT, etc., etc. And there is, as you increase the number of samples for training, you get better performance. And you know, this sort of standard. And you can train with more data, and at a certain point you will reach a plateau probably. But the important thing is that you get this type of behavior. Now, if you, on the other hand, start inserting affordances, there's a nice fact. The affordances per se are a lot easier to train because it's a super simple problem. You just have to tell whether given the object you have +1 of the particular graph type. So learning this mapping is super easy. 26 samples are enough. And you don't improve much because there's a confusion you can see from here. There are certain graph types that are basically, let's say, the graph types can be applied to 2 objects. So if you try to recognize the object, you don't know really from the graph type whether it's one object or the other. There's a confusion there. And so the performance will reach, again, a certain level. The nice thing is that once you combine, and these are the reconstructed affordances, which means I don't have the actual affordance, but I reconstruct them from vision, from the same seed features I had before. And again, in this case, it's better if you're data, but the nice thing is that if you combine the 2, so let's say the black one and this one, you get this other one, which is, it does better. So, which means that starting from the same data that is vision, I sort of do a mapping that I learned before, knowing the graph types. Then is enough to generate a set of features that, put together with the visual features, does better performance in recognition. And which is, again, it's interesting because I just, at the end of the day, extracted a different feature vector than what a standard feature vector would do. Nothing different. I mean, there's no magic there. Okay, now the last experiment I'd like to tell you about started basically from this paper by Rizzolat and Habib that, in short, pose or say that Broca's area is the homologue of F5 in the monkey. So you should expect to find mirror responses in Broca's area. But Broca's area is also responsible for speech, the control of speech in humans. And so we thought maybe when you recognize phonemes, you apply a similar principle. You use your knowledge of the generation of the production of speech for improving the classification. And this was also another TMS experiment by the group of Aliga. And basically what they done was to stimulate different places in the primary motor cortex responsible for the movement of the lips and the movement of the tongue. And also presented stimuli that included, let's say, phonemes that require the movement of the lips, this B and P, and phonemes that require the movement of the tongue towards the teeth, which are these called delta phonemes, T and D, for example. These were corrupted by noise, because otherwise it's too simple, even if they do the TMS considered result. What they found was basically this, that the application of the TMS in the same location, let's say of the, so if you stimulate the lips area, location in the brain, in the primary motor cortex, and you listen into a labial phoneme, you have, for instance, if you measure reaction time, you have a lower reaction time. So you're affecting specifically your perception of that particular phoneme by stimulating the motor area, which is, I think, is an interesting concept again. The opposite is true if you stimulate the different places, like the tongue area here, and the reverse happens if you listen into a delta phoneme. This means basically there's a causal connection between the stimulation of that particular location and your perception of a particular phoneme, and this is specific. So we say, why don't we do the same in, let's say, computational terms? So when recording, like I showed here, movement of the tongue, lips, and head in a number of subjects, they volunteered very happily to get the tongue glued with the coils for recording the position of the tongue, which was very annoying, I suppose. And we tried to build again a classifier for the phonemes, B, P, D, and T, as in the TMS experiment, by also, basically by combining audio features and motor features. So, and then building the classifier as before. To cut a long story short, also otherwise don't have time, is the audio to motor mapping recovered from the data acquired with this magnetic tracker on our subjects. This is just an example of the accuracy we get. So it's not perfect. So the blue lines are the original data and the red lines are the approximation. So you see there are glitches here and there. And this may account for the fact that you don't get super performance at the end. So we did a bunch of experiments. The first one, if you do purely audio classification, this use standard speech recognition features. So also for comparison with existing systems. This is the real motor data. So if we had access to real motor data, it would be super good. This is the reconstructed motor data alone, and if you combine the two, you get this, which means we can improve performance with respect to the audio only classification. And again, here is reconstructed motor features. So we actually take these, extract the motor features using this mapping, and build the classification on the say, a vector that includes both the audio features and the reconstructed motor features. This is to show what happens in various cases, like when you have training on 5 speakers and let's say testing on 1 speaker, or also a possible case where you have only 1 speaker that you have access to motor information, that is yourself, and you try to recognize other people you never heard before. And you see there's always an improvement. This one and this one, you improve on their classification. In this, I think the most interesting point is that if you look at the performance, while you add noise to the literary data, you see that these are the grades. You add noise, so performance goes, degrades, but it's not as bad as with the audio alone. So you get an increased robustness to the initial ones. And okay, just to conclude, this is basically where we're going with this activity. These were all toy problems in a sense. We now have a full, complete speech recognition. For now, it's only at the phonetic level, which means we don't have language models on top. We don't have higher order statistics on the phonemes or on the particles or chunks that we're using for the recognition. But we compared, there's a variety of ways you can do the mappings, these neural networks. Again, we tried many different things, but just to tell you, the end of the day, so this is a state of the art. And on a particular data set, which is a data set that includes, luckily for us, also the recording of the tongue and the lips, so we can do the same type of experiments that we did in the past. And we've been able to show that we can do, if we had perfect reconstruction of the motor feature, again, we improved quite a lot. And this is what we managed to do in this phone error rate. So, which is, I mean, considering these systems are highly tuned, highly specialized, this is not bad. This is using, for instance, HTK, which is an available library. So uses the same tools of HTK to implement the various methods. And this sort of, to conclude, to give a bit of the conclusion to this story and where we like to be maybe in a year approximately, if we manage to. Why this is relevant for the robot, and this is my very last slide, because at a certain point you may want a robot to be able to recognize a particular sentence, even if the sentence is very simple, like please to those dishwasher machine. And there are ways of decomposing the sentence in pieces, but at a certain point you have to figure out how to program the robot to actually do the actions. And so there are many ways where you can use action recognition for telling the robot what to do more specifically. You can use these to teach the robot new actions. And also the robot has to recognize the object. So all this, what I've been saying about object and object recognition is needed. And of course, if we can get better speech, automatic speech recognition, that's also good, because most systems in a situation like this one, unless you're wearing a microphone, nowadays wouldn't work well. And that's it. Thank you.
Thank you very much, Giorgio. One quick question, perhaps?
So one thing, early on you were talking about you obviously using prediction to sort of recognise the action. How similar is that to the kind of models that so this is kind of by Karuna Quanta and Dan Norton, where they did this kind of modular motor learning? They're trying to sort of, do you know that, or is it?
I know that, but that was a more complete system. This was just another way to tell the story of why a particular group of neurons were responding in a certain way. We tried to model two pieces. One was the classification, the other one was the prediction. Just to tell a more complete story about what had been observed in the mind. So I wasn't expecting that one to be as complete as what was modeled. time to actually generate those controllers. In this case, it was purely perception.
Yeah.
Although it contained motor information, but it was only from the perception.
Right, perception part is quite
Yeah.
similar.
I don't know.
You're not looking at
I'm not super, I wouldn't guarantee it. I would have to go and look at the papers to say. No, I know what we've done, but I don't know what Calvato specifically.
Yeah.
Thank you very much, okay?
Thank you.
And, yeah.